This is the first in a series of lectures which are going to introduce you to the topic of chemistry. And in order to get going in our discussion of chemistry, a pretty important question to ask is, what is chemistry? What is it that we are studying? Well, definitions can be kind of tricky, but a good place to start is just to think very basically. Chemistry, we have some intuition, I think, is the study of stuff. We have different substances that we would like to gain information about, and if you want to sound really smart and scientific, you call stuff matter, but matter means the same thing. Matter just means stuff. Well, pressing on with our inquiry, like a petulant child, you tell a child, chemistry is the study of stuff, they're not going to be happy with that explanation. They're going to want to know, all right, well, what's stuff? What is this matter that we're talking about? Unfortunately, we run into some trouble here. That question is actually way too complicated. We're only 2 questions in and we're already out of our depth. So we can probably come to some general agreement on some properties of this matter. We know things are made of it. That's what we usually mean when we say, there's some stuff over there. So that there's some objects comprised of some substance and it has some consistent properties. For example, volume and mass. Now, some people would argue that matter can include massless particles like light. Some others would say that it wouldn't. And since we don't actually know what fundamentally makes up either the stuff that has mass or the stuff that doesn't, then, as mentioned, this is kind of a too complicated answer to be specific about. But we can content ourselves with these kind of vague descriptions and press forward. Don't have to understand everything in science. But we would like to understand more. So how are we going to gain more understanding of what this matter is? Well, what we're going to need is what's called the scientific method. Now, the scientific method isn't the only way that we could study matter. One way that we could study it is we could just kind of sit around and think for a while and see what sort of ideas sprung to our minds and which seemed good and formidable, and then we would expand on those in ways that seemed reasonable and write entire books just sitting at our desk. And believe it or not, that was actually the main mode of scientific inquiry for hundreds of years. So that would be what Aristotle would do, is he would just think about big concepts like the motion of the planets and the stars, and he'd come up with great ideas which had seemingly good reasons, but none of those reasons turned out to be true. So a much better way to do it is the scientific method, which is an empirical approach. And in this approach, we don't necessarily preconceive how everything should fit together. We just start with a piece of it and see if that piece fits the puzzle. So the first thing that we would do is we would pose a question. We're always going to have something that we're motivated to investigate. And then we would propose an answer. Now, this is just a tentative answer. We don't know whether it's correct or not. And we call this a hypothesis. Now that we have our hypothesis, our third step in the scientific method is going to be to test the validity of that answer. And this is called performing an experiment. So now we do something physical, something interactive with the universe, and see if that gives us the result that our hypothesis would suggest. And so we want to predict some logical consequence of our hypothesis and see if our experiment results in that consequence. And whenever we perform an experiment, whatever results we observe, those make up our observations from the experiment. Now finally, we perform our experiment and we see what result we get, and we're going to want to analyze that result. So if it turns out that our hypothesis was false, well, then we're going to need a new hypothesis because our answer to the question wasn't correct, but we still want to find a correct answer. So we come up with a different one. And then we could perform subsequent experiments to see if our new hypothesis was correct. If it turns out the hypothesis is true, and here I'm not going to say true, I'm going to say is not disproven, because we don't actually know that it's true. All we know is that this particular test didn't contradict it. But that doesn't mean if we perform some other kind of test that we aren't going to find, oh, well, our hypothesis doesn't work in this situation. And that would invalidate our hypothesis. So, to try and eliminate as many of those scenarios as we can, we're going to think of a new way to test our hypothesis and see if that holds up. And the more experiments that we can do testing our hypothesis in different ways, the greater our confidence is going to be that it is correct. Go ahead and apply the scientific method to an actual question. So let's say that we want to figure out, how old are the ocean floors? So that's our starting inquiry. In order to gain some ground here, we're just going to go ahead and propose an answer. And maybe we propose 3.8 billion years. That's as old as the oldest rocks which are found in the continents so far. And so that's a hypothesis on how old the continents are. So now we're going to move on to testing that. And so our prediction, maybe if the ocean floors are 3.8 billion years, then we should also be able to find some rocks in the ocean floors which match that dating, just like we were able to find on the continents. And the way we date rocks is we measure their isotope ratios, which tend to change after those rocks form. And they change in such a way that we can figure out how long ago we think those rocks were created. And so we think we're going to find the isotope ratios which match 3.8 billion year old rocks. So we go ahead and collect some samples and we measure those isotope ratios and see what dates we come up with. And now we can analyze the results that we get. The results that we get are that the oldest samples which we can find scouring the ocean floors have isotope ratios which seem to indicate that they're at most 200 million years old. So that disproves our hypothesis that the ocean floors were 3.8 billion years old. And because we disproved our hypothesis, well, now we still want to know how old the ocean floors are, and we can come up with a new hypothesis. And maybe our new hypothesis is that these isotope studies are correct, and so the ocean floors must be regenerated every 200 million years, or approximately that. And that's why we never find a rock which is older. And this is actually true, or at least we think that it's true. We think that the ocean floors get subducted underneath the continents, and then they go back under the earth and are constantly regenerated by magma which flows to the surface. And it takes in some cases as much as 200 million years for that to happen, but you never find ocean floor that's any older than that. So as we continue to apply the scientific method, we're going to eventually wind up with important results which are called laws and theories. Now the starting point for these is our observations. Those were the pieces of data that we collected from our experiments. So for example, I might observe a force on a rock, and I note that it's directed towards the Earth's surface. The rock presses downward, and so that's a single experimental observation. Well, an extension of that would be to summarize a whole bunch of observations. I measure some kettlebells, and I measure maybe the weight of a frog and other things, and I find that all of these objects, they seem to pull downward. And so my law which summarizes that might be that objects are attracted to the Earth's surface or something of that nature. And so a law is going to always apply under the stated conditions. So our conditions might be, it has to be at Earth's surface in this case. It's going to predict the results of additional experiments. So I'm predicting that if I take some other object, I'm also going to detect this force towards the surface of the Earth. And it applies a relationship. So clearly there is something which exists which is causing some attraction between these objects and the Earth. We don't state that explicitly, but a law would tend to indicate that that was the case. So our law might be massive objects attract each other. Or we could state it as an equation, which Isaac Newton did. He said that the force of attraction from gravity is equal to some gravitational constant times the mass of the first object times the mass of the second object divided by the distance between them squared. And this is a little bit of an improvement. This is very specific. Now we not only know that there's attraction, but we know how much attraction if we measure the distance and the masses. So that's actually a little bit better. We can be specific. If you ever have a mathematical relationship, that's going to be a law. Now we can go one step further and have what's called a theory. And so this is an explanation which is given for our scientific results. And this goes further than a law does. It doesn't just summarize them. It answers the question why. Why is it that we observe that these heavy objects are attracted to each other? And something that's really cool about a theory is that we can use it to infer new ideas. Not simply that, for example, that heavy objects attract, but we might be able to make predictions about things which aren't heavy objects because of our implications from our explanation. Now, unfortunately, we can never prove a theory definitively. You can't perform an experiment and observe the explanation itself. You can only observe pieces of data which happen to fit the explanation. The more pieces you observe, the more confident you will be in your theory. But it could always be the case that there's another theory which will also explain the data, but possibly it will explain other data which you haven't collected yet. And so an example of that would be Einstein's theory of general relativity, which attempted to give an explanation to why gravitational effects are observed. And so what Einstein said, was that objects attract each other because they're made out of matter, and this matter causes space and time to curve. But then when these objects are moving through that curved space and time, they get deflected. So for example, here's a picture of the Earth embedded in space-time. You can think of this as a heavy object on a trampoline. When you put it in the trampoline, it causes the trampoline to curve. Now, ordinarily, if you were to roll something on the surface of the trampoline, it's going to move in a straight line. But what happens when it reaches this curved portion? Well, technically, it's still going to move in a straight line, but that's not going to be what it looks like to us. A straight line from us, looking down on this two-dimensionally, we're going to see this thing curving. And to us, it's going to look like it was pulled in towards the Earth, and so it got deflected. Something that's really incredible about this theory is that it's a theory that Einstein came up with to explain why heavy objects fall and attract towards each other. But this implies that anything moving through space-time would be deflected, even something that didn't have mass. And so, for example, a photon, a particle of light, does not have any mass. And Einstein's theory, even though no one has ever done any experiment involving a massless particle, it predicts that it's going to be deflected just like massive particles are. And experiments were performed and observed that this was true. And so that's why we tend to give Einstein credit for coming up with a better theory of gravity, because he's able to explain these new effects which hadn't been anticipated. And this is a feature of theories. You can use them to make new predictions, above and beyond what a law would enable you to do. Let's also look at some statements that we've been given, see if we can identify whether they are an observation, a law, or a theory. So one statement, we have that the sun is comprised of hydrogen gas. Some features of this statement, this would represent the result of a single experiment. We could point our telescope at the sun and analyze the data and find out that it was made of hydrogen. And it certainly doesn't tell us about other stars, such as what Betelgeuse is made of. So since it only gives us a single piece of data, it doesn't make any predictions. That makes it an observation. Now let's say we have the statement, black holes are caused by tears in the fabric of space-time. Well, this tries to explain the nature of black holes. This presumably isn't something we've actually observed. And so since it attempts to give an explanation, it's a theory. And as other features of a theory, it applies to all black holes. It's not just a single observation. It makes a prediction about other characteristics. It might imply that they're portals to other universes or something like that. Well, consider finally the statement, the speed at which galaxies are moving away from us is proportional to their distance from us. Well, this summarizes many observations. We've had to look through our telescope many times at different galaxies and record their velocities and record their distances to arrive at this statement. It even goes so far as to make a prediction for the outcome of new observations, saying that if we look at some different galaxy that we've never observed before, that we're also going to observe this relationship to be true. And so that would tell us it's either a law or a theory, but it doesn't go quite as far as a theory. It doesn't explain why this relationship would exist. It simply asserts that it does. So that means it is a law. Well, the scientific method is certainly a very useful tool. It can do a lot for us. But we also need to be cognizant of the fact that there are some limitations to it. Now, one of the limitations to the scientific method is bias. And people tend to think of a scientific method as being unbiased, but that's not true. One of the ways that bias creeps in is because we choose the questions to ask, and we choose the answers to pose to those questions. Now, what if our human brains are not wired to ask the right questions or aren't wired to come up with the right answers to, for example, explain the ultimate laws which underpin the universe? Well, then there would be no possible way for us to discover them. And we would just have to live with that limitation, even though we wouldn't know we are living with it. And there might be other ways that bias could creep in. We usually try to ask interesting questions. And we have limited resources, so we have to be cautious in how we expend those resources. But that is going to in some way distort our body of scientific knowledge that we come up with. And we can also only ask certain kinds of questions. We cannot, for example, ask moral questions. Science can't tell us whether something is right or wrong. It can't answer questions which can't be determined by a simple observation. But that doesn't mean that those things are not maybe true or untrue. We might objectively say that murder is wrong, but science, it's not something that it could come up with. We also can't prove our explanations. As good as they may be, we are never completely sure that they are the correct explanations, and there's not one that's a smidge better or that's actually the accurate one. Sometimes we prefer simpler explanations, but it's not a guarantee that the simpler explanation is the correct one. And also, even when we perform experiments, our experiments may be incorrect, they may be flawed in some way. And so when we think that we've disproven a hypothesis, we haven't, or when we think we've added support to it, we haven't, because our experiment gave the incorrect result. And we can fix that by repeating our experiments, and the more we repeat it, the more we'll strengthen our confidence. But if we don't do that, then there's the issue that we're going to get some bad science. An example of where this becomes a problem, very recently in 2012, there was a landmark study which was sponsored by a pharmaceutical company. And they're going to invest millions of dollars into producing some anti-cancer drugs. And so they want to make sure they're spending their money wisely. And so they go back, identify some landmark papers which had been done to establish basic facts in cancer research. And they try and replicate those experiments. And they do this for 53 seminal landmark papers. You want to guess how many of those were able to be reproduced? Well, the answer was 6. So 47 out of those 53 papers they could not reproduce. Now, it doesn't necessarily mean that 47 studies were wrong. Some of those might not have been replicated simply because of the chances of the experiments. It might have actually been that the people reviewing it who got the experiments wrong. But this is pretty indicative that there's a problem. And so why does this problem come up? Well, nobody wants to go back and retest research that's already been done before. That's not going to get your name on any awards or any magazines. If you want glory in science, you have to go and discover new things. And so nobody wants to do this really important step of repeating experiments to strengthen our confidence. And so, this is something that we need to be cautious about in applying the scientific method. We have to recognize what its limitations are, and we have to do our best to take precautions to try and limit their impact on our results.